Welcome back. In the previous video on energy and climate change, it was discussed that we need our energy infrastructure that heavily depends on fossil fuels and CO2 emissions to be turned into an energy system based on renewable energy technologies. In such energy transition, renewable electricity like solar electricity will become the dominant energy carrier. So, the learning objectives of this video are to understand the transition. How does a 100% renewable energy future look like? What are typical timescales of introducing new technologies for the energy transition? And how does the energy transition relate to the various scenarios for CO2 emission reduction? So let's get started. Our current energy infrastructure, as simplified in this video, depends on energy carriers as oil and oil products, gas and coal. These primary energy sources are consumed in the various sectors like transport, industry, households, agriculture and public services. Coal and gas are used in plants to convert this chemical energy in either the secondary energy carriers, electricity or heat, to be used in the above sectors. This infrastructure is demand-driven. When industry or household need more electricity, the plants will operate at higher capacity, or in other words, burning more coal or gas. The electricity is centrally and transported in one direction to the industry and households. The storage functionality is within the primary fossil energy sources. These are directly consumed in the sectors like gas and coal in industry, oil products in transport, or converted into electricity and heat to be consumed in the various sectors. Consumption of energy in this system leads to CO2 emissions. The next visual shows a future energy infrastructure in which fossil fuels are replaced by renewable electricity. Wind and solar energy are directly converted into electricity using wind turbines and photovoltaic modules. The electricity supplies all energy needs for households. In certain regions in the world, gas-powered residential heating will be replaced by electrical-powered heat pumps. Fossil-based combustion engines in the transport will be replaced by electromotors. In this system, the dominant energy carrier is electricity. This system is not demand-driven anymore, but supply-driven. The energy generation depends on when the wind is blowing and the sun is shining. In such energy system, storage of energy becomes an important factor as well to guarantee the reliability of the energy supply. Electricity generation has been decentralized. Many wind parks, solar parks and photovoltaic systems integrated are installed on many locations onshore and offshore. Transport of electricity becomes more complex. The electricity grid has to facilitate bi-directional electricity transport as well. Is such transition possible? Let's start with an inspirational example. A detailed model entitled Global Energy System based on 100% renewable energy was published by the Energy Watch Group and Christian Breyer of the LUT University in Finland. This model simulates global energy transition for all regions in the world in detail from 2015 towards a 100% renewable energy system in 2050. This model does not need carbon capture in the second half of this century to meet the targets of the Paris Climate Agreement. This is in great contrast to the IPCC CO2 emission scenario towards 1.5 and 2 degrees Celsius temperature increase at the end of this century, as we discussed in the previous video. The year 2015 acts like the reference starting point here. In this year, the primary energy sources are heavily dominated by the fossil fuels like oil, coal and gas, with a minor contribution of nuclear and biomass energy. The model uses existing renewable technologies like photovoltaics, wind turbines, batteries, heat pumps and electrolyzers. By replacing this energy structure, the model shows that to realize a 100% renewable energy system, the role of wind and solar electricity has to grow significantly. In other words, 80% of the energy in the form of renewable electricity is supplied by wind energy and 69% by solar energy. A minor complementary role is for biomass, hydroelectricity and geothermal energy. It demonstrates how in time electricity will become the dominant energy carrier and replace fossil fuels. In 2050, 90% of the energy supplied is electricity. What are the costs of such transition? This graph shows that the levelized cost of energy can stay under 60 euro per megawatt hour. The cost price consists of CAPEX, OPEX fixed, OPEX variable, grid costs, fuel costs and CO2 costs. CAPEX stands for capital expense and covers fixed assets such as building, equipment and land. OPEX stands for operating expenses and is the ongoing cost for running a business of system. Here a distinction can be made. OPEX fixed are the running costs regardless of how much business is made, whereas OPEX variable are running costs that change with the amount of business. The figure shows that by the introduction of renewable technologies, fuel and CO2 costs are phased out while CAPEX of the renewable technology is increasing. It is an inspiring model that demonstrates that with an existing technologies, a transition towards a 100% global renewable energy system is technological feasible at no additional costs. Let's consider again the energy infrastructure of the European Union in the year 2023, visualized in this Sankey diagram we have used before. Energy transition, what does it mean for this diagram? Phasing out fossil fuels. Let's remove the primary energy source based on fossil fuels like gas. And let's remove the primary energy source based on fossil fuels like coal. And let's remove the primary energy source based on fossil fuels like oil and oil products. Not much is left. It means that many of the current infrastructure should be replaced. How should the future energy structure and corresponding Sankey diagram look like? Again, I will use an example of the European Union system, and this time it also includes the UK. And I constructed a Sankey diagram out of the future energy system of 2050 as described in great detail by the Christian Breyer group of LUT in Finland. This model is published in the article in the Progress of Photovoltaics Research Applications as shown here, and looks completely different than the reference we used so far for the energy infrastructure Sankey diagram in 2023. In this paper, a technology-rich energy system model was applied in hourly resolution for Europe in 20 interconnected regions and in full sector coupling covering all energy demands. The results reveal a cost-neutral energy transition towards 2050 based on declining the levelized cost of electricity. If we consider the primary energy sources, the generation of renewable electricity will be the most dominant primary energy source. In this model, the contribution of solar energy is estimated to be even 61–63% of all primary energy sources in Europe. As shown, renewable electricity is a dominant energy carrier that directly supplies the sectors. The conversion of a primary energy source into a secondary energy source will be not focused on generating electricity anymore, but on the generation of green synthetic fuels. Green synthetic fuels, also called e-fuels or electrofuels, are made from captured carbon dioxide and or green hydrogen produced using renewable electricity, solar, wind, hydro, creating a virtually carbon-neutral energy source that can power existing engines and infrastructure. They are a low-impact alternative to the current fossil fuels, suitable for hard-to-electrify sectors like aviation and shipping, as they don't compete with food crops and can use existing fueling networks. A primary energy source will be environmental heat as well. Environmental heat refers to the thermal energy in the surrounding atmosphere, the geothermal energy, which is the thermal energy within the earth, and the thermal energy in oceans and lakes. The future energy systems will use environmental heat through technologies like heat pumps, air and ground source, and large-scale district heating networks powered by diverse renewables like solar, biomass, and waste heat. Leveraging thermal energy storage, to buffer intermittent renewables and manage grid load, integrating excess renewable electricity into heat and recover industrial waste heat, all aiming for decarbonization and efficiency. An important role in the interplay between the solar, wind, hydropower, electrolyzers and heat pumps will be the storage. Battery storage enables the diurnal use of PV electricity and supports wind's power balancing. Heat pumps contribute some flexibility in combination with thermal energy storage. Electrolyzers contribute to major flexibility in the energy system in transferring not directly used electrons into molecules in a first step in the form of hydrogen, which is buffered in hydrogen storage for subsequent near baseload conversion into electricity or as a source for more complex e-fuels. As you can see, electricity, heat and synthetic fuels are coupled. This is referred to as sector coupling, which is the integration of energy sectors, electricity, heating, cooling, transport, industry to create a flexible, efficient and decarbonized energy system, primarily by using surplus renewable electricity to power other areas, transforming it into hydrogen, or using power-to-X technologies for heat, fuels or industrial processing, shifting away from fossil fuels. It enables the use of excess wind and solar power, balancing supply and demand and making the whole system more resilient and sustainable. The model shows that on the generation side, the capacity of installed wind and solar electricity generation has to grow drastically. Is such quick growth possible? I will discuss that in part 2 of this video. So see you back.